available. I already posted them in the Slack somewhere. Basically talking about what we can learn about the generation of magnetic fields inside stars from just looking at their surface properties. So let's see if this works. Yeah. So I think it's fair to say that we're quite limited with what we can learn from stars, stellar magnetism, based on the surface properties alone. We can't see inside stars. Even astroseismology, the kernels for astroseismology are often quite limited towards the surface. So we can't really probe the depths at which the magnetic field is being generated or regenerated, the toroidal field, which emerges later on to become spots and powers, flares and coronal mass ejections. And so it's key that we understand better the generation of magnetism inside stars, because it's a driving factor in how the rotation periods evolve for sun-like main sequence stars, the impact that it has on exoplanetary atmospheres and things like this. And more close to home, it's really important that we can make predictions about how active our own star is going to be for our infrastructure that's in orbit around Earth. So just to mention quickly, I'm funded by the ERC Wholesome project, which is a collaborative effort between multiple host institutions to try and kind of bridge this gap in modeling, where essentially there are people modeling the interior of the sun, there are people modeling the atmosphere of the sun, and we're essentially trying to do a coupling of the two and develop new codes that are capable of doing that kind of thing. So let's look at what kind of things we can observe at the surface. We can observe things in white light, so spots. We can observe the radial magnetic field. We can make butterfly diagrams that I don't think I really need to explain, but here's the last few solar cycles of butterfly diagram, where we see the average, longitudinally average magnetic field of the sun plotted versus latitude and time. We can see the sun's butterfly diagram and the polar fields reversing. If we make a little, I always show this, like an update every time I make a presentation. This is the current solar cycle, cycle 25, with the last average monthly sunspot number highlighted in red, compared to the last two solar cycles. So we can see the current solar cycle we're on, we would say is kind of like a middle of the road cycle between the two. And then out of nowhere, bang, we have a nice big burst of activity. So what we really need to do is understand what's happening inside the sun itself. So we need to understand how the magnetic field, the toroidal magnetic field, is being generated inside the sun and quantify it. And so in general, we think that we have this differential rotation that's inside the sun. It's acting on a toroidal magnetic field. It's twisting the field, and we're generating a toroidal field in one direction in one hemisphere and the other direction in the other southern hemisphere. And that kind of goes into this picture that we have for the sun's or stellar dynamos in general, where we have the conversion of toroidal field into toroidal field, and then toroidal field back into toroidal field by the emergence of magnetic flux and back. So one method that was proposed by Robert Cameron collaborators is quite a nice basic principles kind of thing, which is to say that consider that we want to evaluate the toroidal magnetic field in a given hemisphere of the sun. So we can pick the northern hemisphere here. Then just kind of like first principles analytic calculation, if we consider Maxwell's Faraday's induction equation, so we have the rate of change of B equivalent to the curl of an electric field, and we then substitute that into an equation. This is the only part, the mathsy part, by the way, for people who don't like maths. We substitute that into the equation for the rate of change of the magnetic flux in a given hemisphere. But because we have a curl here, we can use Stokes' theorem to instead evaluate the currents that run around a contour in that hemisphere. So you can think of it like a Biot-Savart kind of style thing. And then we can make clever assumptions, clever choices about where we put this contour. So we have one contour that's running along the surface, one contour which we can put at the equator, and we can move into the rotating frame of the sun, so we zero out this contour. The bottom contour we can put deep into the radiative zone, so we're well below where we think the toroidal field is being generated. And the top one we have just running through the axis. And so this contour essentially should encapsulate all the field that's being generated, the toroidal field of that unipolar sense that we have in the northern hemisphere. And so we can avoid calculating C, D, and A and just focus on D, which is something we can calculate. And so this is written here in terms of the large scale V cross B, so velocity across the magnetic field, and the turbulent V cross B. and then currents as well. And so let's do that very quickly for the sun. So we have the magnetic butterfly diagram here, which is RB. RV is going to be the differential rotation of the sun, so I have the profile plotted there. We multiply these two things together to get our integrand that's going in here. And then if we just divide this plot in two and sum the contour in the north and the south, we can get our toroidal generation, toroidal field generation as a function of time. And so we can see basically that when we have a minimum, we have the dipolar field and the differential rotation profile, and that is twisting up, this is giving us a constraint on how much toroidal field can be produced by the field in the convection zone. And so this peak here is essentially the flux that's being generated at the base of the convection zone, which will, during cycle 24, now emerge and then be replenished and go around in a cycle. So the question is, so we have this picture where we're just using observations. We actually have not got a way to test this because we can't see inside the sun. And so what we did is we used existing MHD dynamo simulations to perform the same calculation, but where we know the flux that's inside the contour, and we can evaluate all of the contours and change the depth of the integral and all these kind of things. We're also looking at the emergence of dipoles in these simulations to look at the tilting of active regions and things like this, but I'll leave that for later for discussion. And so this is kind of an overview of the simulation. This is our butterfly diagram. You might notice it's kind of a little bit different to the sun's butterfly diagram. It's not exactly a solar analog. But if you look at the toroidal field at the base of the convection zone, you can kind of see this butterfly diagram pattern that we had before. So just to kind of convince us that we're using a reasonable model to do our tests. And so here's our butterfly diagram of the radial magnetic field. Here's our differential rotation pattern at the surface. And so here's the thing that we're going to integrate in order to get our toroidal field generation. So the solid line. So let's focus on the solid green line. The solid green line is what you get from doing the process that I said before. We just sum up in each hemisphere what's happening versus time. That's what we get from our surface method. The dashed line that's underneath is showing you what you get if you do the full true calculation of the toroidal flux. And then the two colors are just the north and the south. And so you can see in general that just using information that we have at the surface of the model, we can pretty much get most of the generation of the toroidal field that will then go into the dynamo and have the cycle. But there's these epochs here where we have a disagreement between the value we get from just looking at the shear of the field and the true value in each hemisphere. And so if we then do kind of a synopsis of all of the line segments that we have going around the contour, and we do a bit of a budgeting, if we just look at the surface terms, this is the production of toroidal field that you get from in total is on this top bar here. Then from the large scale field is here, the small scale fields is here, and then the currents is here. You can see that the locations where we had a departure from the surface method coincides with where we have currents in the model. And essentially what we found is that these currents are due to the fact that near the surface of the model, there's a boundary condition that requires that the radial flow tends towards zero. And so if you imagine in a real star, you have the toroidal field that's building up, it's going to bubble up and it's going to emerge through the surface. In the model, it can't actually emerge through the surface because the boundary condition prevents it. And so instead what it does is it diffuses through the surface. And so that's completing the dynamo loop. And so actually what we're seeing in that diagram is the cycle of the magnetic flux moving from toroidal back to ploidal at those epochs. So the method works fine. We can also do a few tests where we change the depth of the integration, so we can scan through the convection zone. So here's the depth of the integral versus time along the x-axis. And so you can see as we change the depth of the integration, nothing is changing because we're containing the zone where the toroidal field is being generated, so there's no change. Okay, we can see that that the large scale field is where the base of the convection zone is where the field is being generated. Here we can see what I was scanning through it, and you can see here, if you look at the very top of this, this is the magnetic diffusion term, that this is the thing that's causing a difference between the predicted value from a large scale field and flow and the total value when you get to the surface. Okay, and so to summarize, we basically tested this method from Cameron collaborators, and we found that it's actually doing a very good job at estimating the generation of toroidal field at the base of the convection zone. And all you need to account for is the fact that you're also losing toroidal field through the surface boundary due to active region emergence. Okay, that's it.
Quick questions over there. Just speak loudly if you don't have mics.
All right. So you showed from observation that the generation of and the peak seems to come the energy of support and acceleration.
Precisely, yeah.
Does that give you a normal taste?
Yeah, so he's asking the fact that there's a difference in when the peak toroidal flux generation and the peak of the actual emergence of active regions, if that's corresponding to the difference in the lag time between the active regions emerging. I would say it's more a reflection of the fact that we can just tell you about the generation. So I guess, yeah. So this is just a measure of how much is being generated, but then you would assume that there's a critical amount of field that you need to have at the bottom for it then to start emerging. So yeah, I think so. The interesting thing though is that you get this peak before you start the cycle, so you can make a prediction, right? You can actually say like, okay, well, we think this, given we have this amplitude here, when we get the cycle 26, you can now make a prediction. You could say, okay, it's going to be this strong. I know. Okay.
Thank you very much.